Hello and welcome to this screencast, which is intended as a sort of pre-reading before the session on titanium alloys. So it's intended to introduce the main topics that we're going to cover. And what I'd like to do is talk very briefly about the main advantage of titanium and why it's used in aerospace applications, and then talk a bit about the main alloying elements and the effect that they have. So if we look at our now familiar table of approximate properties for our different alloy groups, we can see immediately that strength is a major advantage of titanium. We can, with appropriate alloying and heat treatments, get it up to very high yield strengths. In terms of density, we've got a material that's quite a bit denser than aluminium, but significantly lower density than most steels. And that's really where the advantages come. It's not just the strength, but also it's the fact that the density is significantly lower than steels. In terms of cost, titanium is an expensive material, but the benefits of the performance make it worth that expense in some cases. It's also worth noting that the fracture toughness of titanium is high as well, and that's important for highly loaded structures within the aircraft. If we look at the specific strength, so the strength divided by density, we can see the advantage of titanium a little bit more clearly. So we've got an index number here of 0.29 for titanium alloys. We can see that's quite a bit higher than aluminium alloys and very much higher than medium carbon steels. Higher grades of steel can get a little bit more competitive with titanium alloys, but still there's a significant advantage to titanium. So one of the interesting bits of metallurgy about titanium is that pure titanium, before you add any alloying elements, can exist in two different crystallographic forms. An alpha phase, which is hexagonal close packed, and that's stable up to 880 degrees C. So that's the phase that pure titanium would be in at room temperature. The other important phase is a beta phase, which is body-centered cubic. One very important thing is that this alpha phase is nothing to do with the alpha phase that we use to describe the alpha phase in aluminium alloys. It's just that phases are usually called after Greek letters. So don't get confused about the fact that we're using alpha here where we used alpha in terms of aluminium alloys. They're completely different. So at low temperature we've got an alpha phase, and at high temperature we've got a beta phase. And our alloying elements and our heat treatments in this case are basically playing around with the distribution of those two phases that are present in an alloy. So with one notable exception, the heat treatments are not doing the same as they are in aluminium. They're quite different. We're manipulating the presence of two phases. It's a bit more similar to steel metallurgy, if you're familiar with that. So this basically allows us to produce alloys in four main groups that are called alpha, near alpha, alpha beta, and beta. And in short, we would select these four groups. For alpha, we'd select it when we're looking for properties like corrosion resistance that aren't so important structurally. We'd select a near alpha alloy where creep resistance was what we were looking for. Our alpha beta alloys give us the best all-round properties, the best compromise if you like, and the beta alloys give us the highest strength. And in the session and the next session we're going to go through why that is. Here's an example of a phase diagram of titanium when alloyed with alloying elements that are called alpha stabilizers, and the most important ones of these are aluminium and oxygen. So what these do as you add aluminium or oxygen is they stabilize the alpha phase. They make the temperature at which it transfers to beta go up. So you'll have more alpha in your microstructure. They also act as solid solution strengtheners as well. Tin and zirconium also are solid solution strengtheners, but they don't change the transition temperature significantly. So they're known as neutral elements. So the alpha stabilizers, aluminium and oxygen, stabilize that alpha phase, so they push up the transition temperature as we add weight percent of the alloying element. In contrast, beta stabilizing elements are things like molybdenum, vanadium, copper, silicon. And these are in two different groups. Molybdenum and vanadium are called beta isomorphous alloys, and they produce a phase diagram that looks like this. So basically, as we're adding alloying element, the beta phase is becoming stabilized. You're more likely to have beta in your microstructure than just alpha. Beta stabilizers also tend to improve the workability of an alloy because the BCC phase is more ductile. And two very useful heat treatment approaches are basically allowed by this shape of phase diagram. Copper and silicon are different. They're beta eutectoid, so they still stabilize the beta phase slightly. But we get a phase diagram that looks like this. And this should look vaguely familiar to you because it looks a little bit like the aluminium eutectic phase diagram. And sure enough, as we get into it, we'll find that we can manipulate this in a similar way to aluminium for one particular group of alloys. So that's really the important difference. We're going to go into more detail in the session itself, but the things to take away are we've got some alpha stabilizing elements that stabilize the alpha phase, which is the hexagonal close packed form of titanium. And then we've got some beta stabilizing elements which stabilize the beta phase. So it makes it more likely that you're going to get this beta phase BCC arrangement in your alloy. And manipulating these two and applying heat treatments are basically what we do to get different alloys in the titanium system.